Today is May 12th, and we're going to solve trig equations, okay? And it's TEI 3 today, all right? So the first example is simplifying, combining fractions, and using identities. So what we want to do is simplify this. So we're not going to get into the solving quite yet, okay? How do we combine these, right? So these are two fractions, right? So we need a common denominator, okay? So what does this one need? This one would need a cosine x, and this one would need a 1 minus sine x, okay? So that's what I'm going to do. I'm going to multiply by a version of 1 that would get me a common denominator, and then I'll be able to subtract these and make it one fraction, okay? So we have cosine of x over 1 minus sine of x, okay? And I'm going to want to multiply that by cosine x over cosine x. So I'm going to do it in red to show you that, okay? And then minus sine of x over cosine of x. And I'm going to multiply this one by, this one needs the 1 minus sine x denominator, right? So I'm going to multiply by 1 minus sine x over 1 minus sine x. Okay, so then when we multiply these, we're going to get cosine squared x, right? So this is equivalent to cosine squared x over, and then this would be cosine x minus sine x cosine x. Okay, and then minus, and then this would be sine x, okay, and then minus sine squared x, all over cosine x minus cosine x sine x, or sine x cosine x. Okay, so now I have a common denominator, right? So now I'm going to subtract this numerator minus this numerator, okay? So I would have cosine squared x, and then I'd have to subtract both of these, okay? So it'd be minus sine x, and then I'd have to distribute this subtraction, right? So this becomes plus sine squared x, all over cosine x minus sine x cosine x, okay? Now, we're going to look for identities now, okay? So if you look at this, okay, this cosine squared x plus this sine squared x, those two together make 1, right? So I could rewrite this as cosine squared x plus sine squared x minus the sine x all over cosine x minus sine x cosine x. These two make 1, right? Because cosine squared x plus sine squared x is equal to 1. That's from yesterday, right? So I'm going to write that off to the side here. Cosine squared x, I'm using this identity, plus sine squared x is equal to 1. So this can be swapped out with 1. So this is equal to 1 minus sine of x. Okay, so that simplified a little bit, right? I'm going to slide this up a little bit. Okay, now down here, what can we do? Well, we could factor out a cosine x. And then what we'd be left with is 1 minus sine x. Now, we're not writing this, but you know what's up here? This whole thing multiplied by 1, right? Okay, so now this is 1 minus sine x over 1 minus sine x, right? Those make a 1, right? And this is a product and this is a product, so we can cancel, right? Right? Okay, so we get 1 over cosine of x. And what is 1 over cosine x? Well, that is secant x. So that's our answer. This is equivalent to secant of x. Okay, so all of that, this fraction right here that we're subtracting, these two fractions, right? It all comes down to just being the same as secant of x. Okay. All right, let's go to example number 2. Okay, so for this next example, I want to be able to simplify using identities, and then we're going to use factoring and canceling. Okay. So a lot of this factoring and canceling that we've done in previous units that weren't with trig functions is going to play into here. Okay. All right, so we want to write each expression as an algebraic expression of a single trig function. Okay, so this is just going to be a trig function. Okay. All right, now whenever you see a squared trig function, you should be thinking, Pythagorean theorem, or not Pythagorean theorem, Pythagorean identity. I said the wrong thing. Okay, you should be thinking Pythagorean identity. Okay, so which one is this, right? Well, remember cosine squared x plus sine squared x is equal to 1. That's really the one that I really you have to know, okay, down pat. Tan squared x is a modification of this, right? So if I divided, okay, by cosine squared x, this sine squared x would be over cosine squared x, which would make a tan squared x. Okay, so that's how I'm going to get this tan squared x. I'm going to get this tan squared x by dividing each of these by cosine squared x. What happens when I multiply or divide this by cosine squared x? I'm going to get 1 plus what happens when I divide this by the sine squared x by cosine squared x? I'm going to get tan squared x. That's not an x, that's a little asterisk, okay? And then equals, and I divide this one by cosine squared x, and that would give me secant squared x, right? So how do I get tan squared x? I don't have what tan squared x is equal to yet, right? All I'd have to do is move this 1 over to the other side, okay? So that means this tan squared x is equivalent to secant squared x minus 1 over secant x plus 1. Secant squared x minus 1. This is 1 is a perfect square. This is a difference because we have a difference, and these are both perfect squares, okay? That means this factors into secant x minus 1 times secant x plus 1, right? Over secant x plus 1, right? And we could put parentheses around this. And there's a 1 right here that we could write. And then this secant x plus 1 and this secant x plus 1, right? They cross out, they cancel because this is a product and this is a product, right? So this one and this one are going to cancel and make a 1. And we're left with secant x minus 1 over 1, which is just secant x minus 1. And that's what this is equivalent to. You couldn't break this down anymore, okay? Going from here to here, I want to point this out. Okay, this is an algebraic identity that we use, okay? Whenever you see a squared minus b squared, that's always going to be equal to a minus b and a plus b, right? That's an algebra identity that we use a lot, okay? We're doing trig identities, okay? These are always equivalent, okay? All right. And that's what allowed us, this is really 1 squared. That's what allowed us to write this numerator the way we did, okay? All right, let's go to example number 3. Okay, so here we're going to get into the trig equations, okay? So we've done these are going to come down to being very simple trig equations, but they're not yet, okay? We're going to get them down to that, okay? All right, so here we go. Okay, find all values x in the intervals 0 to 2 pi. So we only want positive angles where these would be the same, okay? All right, so right off the get-go, okay, what I'm going to do is I'm going to clear out my fractions, okay? And so I'm going to multiply both sides by sine of x, okay? Now, there's one thing we got to be aware of at the very beginning. Sine x right here, this denominator from before, it cannot be 0, okay? It can't be 0. So sine of x cannot be 0. So whatever angle causes sine x to be 0, it cannot be one of our answers, okay? Because of the way the equation is written, right? We'd be dividing by 0 then, okay? So right now I'm going to multiply both sides by sine of x, okay? So if I multiply this left-hand side by sine of x, I'm going to wind up with cosine cubed x is equal to cotangent x times sine x. Okay, how do I solve this? Okay, really what you want to do when you're solving trig equations is you want to get down to one trig function. That's it, okay? So how can we change stuff? Because right now we have 3 trig functions, okay? So what we can do is we're not going to change this one. This cotangent x is an identity, right? Cotangent x is cosine x over sine x. So I can replace that, okay? So that's what we're going to do here. So cosine cubed x is equal to, and then this is cosine x over sine of x times sine of x, okay? And what we used is the identity that cotangent from yesterday, cotangent theta is equal to cosine of theta over sine of theta, okay? And instead of having theta, we have x in the theta spot, okay? But it doesn't matter. It's whatever's in that spot, it's the same, okay? Now what happens here? I'm multiplying, have cosine x over sine x times sine x. My sine x's are going to cancel. And then I'm left with cosine cubed x is equal to cosine of x. Okay? Now, what can we do next? Well, I notice, okay, I have cosine x's on both sides. I'm going to move them all on one side, and that's going to allow me to factor it out, okay? So this is going to be cosine cubed x minus cosine x is equal to 0, okay? One thing we cannot do, okay, because you don't know what cosine x is, we can't divide both sides by cosine x, okay? You can't do that, all right? Because you don't know what cosine x is, okay? And because you don't know what cosine x, you could be inadvertently dividing by 0, okay? So you can't do that. The way to fix it, you lose answers basically, okay? The way you fix that is you move it over and then you factor it out, okay? So what we're going to do here is we're going to factor out a cosine x. So cosine of x times if we factored a cosine x out of this, we'd be left with cosine squared x minus 1 is equal to 0, okay? So what can happen here is cosine x could equal 0. We're going to use the 0 product property. We have a product here, cosine x times this is equal to 0. So one of those two things must be 0, okay? And that's the 0 product property. So cosine x is equal to 0, or cosine squared x minus 1 is equal to 0. Okay, so this one's ready to solve, right? This is just a simple trig equation from the last unit, okay? This one we could add 1, okay, and we get cosine squared x is equal to 1. And then we would square root both sides. And remember, cosine squared x like this means cosine x times cosine x, right? So cosine squared x is equal to the square root of 1. This would be the absolute value of cosine x is equal to 1. Okay, and what could this be? Well, this means that cosine x could be either plus or minus 1. Okay, so either cosine x is equal to 0 or cosine x is equal to 1 or negative 1. Okay, so what happens? Where is cosine x equal to 0? Okay, so this one, solving this one, where is cosine equals 0? Well, this ratio, right? This is our ratio, the 0, right? Is when it's x over r, right? So it's going to be 0 when x is 0. So that's going to happen on our unit circle. That's going to happen at this angle right here and this angle right here, okay? And so this has coordinates 0, 1. This point right here would have coordinates 0, negative 1. Remember, my r is equal to 1. So my angles of rotation would be this angle, or if I kept going, this angle. Okay, both those two angles would produce a cosine ratio that would be 0. Okay, so what does that mean this x is? Okay, so this x could be pi over 2, because that's what this angle is, or 3 pi over 2. Okay, now how about this one? Where could cosine x, where could the ratio be 1? Well, the cosine ratio could be 1 right here, okay, or it could be negative 1 right here, because right here x would be 1, y would be 0. Here x would be negative 1, y would be 0, and r would equal 1, right? So the answer to this one would be this angle, which is angle 0, or this angle, right? It could be this one right here, or we could go to this one. It's hard to show that terminal side right here. When the initial side and terminal side are the same, that's kind of hard to show, right? because there's no rotation, so you don't see an arrow right here. But it'd be this one right here, which would be angle 0, right? And this angle would be pi. Okay, now, so those are two answers. These are 4 answers to this equation, right? 2 of them don't work. What? Why? Why? Well, back up here, what did we say? Sine x cannot be 0. The sine ratio cannot be 0. The sine ratio is 0 when y is equal to 0. Well, would it be these two that don't work? Nope. Would it be these two that don't work? Yep. These two do not solve this equation. Why? Because they make this denominator become 0. Okay, and then we're dividing by 0. So guess what? These are called extraneous solutions, okay? And we can't use them, right? All right, so our only answers are, the final answer is x is equal to, let me slide this up. So I cross those out, okay? So the only answers are x is equal to pi over 2 and 3 pi over 2. And those are the only 2 angles where cosine cubed x divided by sine x is equivalent to cotangent x, okay? There's only 2 angles where this happens, those 2. Okay? All right, let's go to example number 4. Okay, so this next example, we're gonna solve this by factoring, okay? And if you look, this takes on what's called quadratic form, okay? And we've talked about that before, right? But this is another form of that thing called a quadratic form, all right? Because you have a squared term, you have a regular term, and then you have a number constant, right? So what we want to do is to factor it, we got to get one side equal to 0, okay? So I'm going to move this 1 over to the other side, okay? And I'm asking you for all the solutions. So not just the ones between 0 and 2 pi, but all of them, okay? And I'll talk about that in a minute. We'll get the ones from 0 to 2 pi first, and then we'll get all of them, okay? And I'll show you how we do that, okay? So we need to move this 1 over to the other side. So this would be 2 sine squared x plus sine x, okay, minus 1 is equal to 0. Okay, this is like, I'm going to put off to the side here, this is like 2x squared plus x minus 1 is equal to 0. Okay, so that's why we call this quadratic form, okay? So how would we solve this one? We would solve it by, making an area model and factoring it, right? Okay, so here, what we have to do is find 2 numbers whose product is -2. So I'm going to do it in red. So product is equal to -2, and the sum would have to be +1. And what 2 numbers would do that are +2 and -1. When you multiply those, you get -2. When you add them, you get 1. Okay, so I'm going to make my area model. Okay, so we got to make it a little bit bigger than normal, okay, because we got to write trig function in here. So this is 2 sine squared x, and this is -1, and then this tells me we're going to have 2 sine x, and here we're going to have a negative sine x. Okay, so GCF across the top is a 2 and also a sine x, so this is 2 sine x. And 2 sine x times what would give you 2 sine squared x? Well, this would have to be a sine x, right? So sine x times what would give you negative sine x? Well, it would have to be -1. And 2 sine x times what would give you 2 sine x? +1, right? And then 1 times -1 is this -1, right? So this factors into this sum and this difference, right? Being multiplied together. Okay, so back over here, this becomes 2 sine x minus 1 times sine x plus 1. And are you starting to see that a lot of the stuff that we've built over the year is coming into play here, right? Okay, that's why this is like the last unit we do in the year, okay? Because everything we've done kind of built up to this has come to being able to do these problems, okay? All right, so this is a product and it equals 0. The only way for that to happen is one of these 2 factors is equal to 0, okay? And there's no restrictions like the last problem. We're not dividing by anything, right? So there's no restrictions on this one, okay? So whatever we get is what we're going to get, okay? So 2 sine x minus 1 is equal to 0, or sine x plus 1 is equal to 0. Okay, solving both these for sine x, okay, we'd have to add 1 and divide by 2. So this would be sine, let's just go through and do it. Okay, so 2 sine x is equal to 1, which would mean sine x is equal to 1/2. Over here, sine x is equal to -1. Okay, and now, okay, so where would this happen? Okay, so this could happen from 0 to 2 pi. Where's the sine ratio positive? Well, it's in the first quadrant, because all the ratios are positive in the first quadrant, or in this top left quadrant, right? The sine ratio is there, positive there too. Okay, so this means my y is 1, and my y is 1 here, and this means my r is 2 and 2. This x right here would have to be positive square root of 3, and this x over here would have to be negative square root of 3. And the angle, the reference angle right here of this triangle, what's always opposite 1? It's always pi over 6. Okay, so this is pi over 6, and this angle is also pi over 6 because it's opposite the side that's 1. What's the angle of rotation? Well, the angle of rotation would be pi over 6. And if we went all the way to here, there'd be 6 pi over 6, but that's too much rotation, right? We gotta back off this much, right? This pi over 6. Okay, so this is one of the angles of rotation, or this one, right? But if we go all the way to here, that's 6 pi over 6, right? If we go all the way to the negative x-axis, that's 6 pi over 6. I've got to back up a pi over 6. So this would be 5 pi over 6. Okay, how about over here? Where is sine x equal to -1? Well, this is a ratio, and it's -1 over 1, right? So it's -1 over 1. That would mean my y and my r have to be the same size, right? Okay, so where's that going to happen? It's going to happen right here. Right there, my angle is, or my x is 0, my y is -1, and my r would have to be 1. Okay, so what's this angle that I would rotate around to? And it would be right here. Okay, now what is that angle? That angle is 3 pi over 2. Okay, so here we go. Those are the 3 angles that would cause this to be true, okay? Now, we know we base it off of sine, right? Okay, and we know that these angles are going to repeat as we go around and around and around, right? A full rotation, and I'd be back to here, and that'd be a solution. That'd be another solution, but it'd be bigger than 2 pi, right? And I could keep going around and around and around, okay? Now, what happens is I could do multiple rotations of 2 pi, and that would take me back to these terminal sides, right? Okay, so we actually have 3 answers here. We have x is equal to pi over 6. Okay, that's only one answer. But if we do full rotations back to this terminal side of pi over 6, okay, we can get multiple solutions to this. So what we have to add is 2 pi in. Why 2 pi? Because the period of sine is 2 pi. It repeats every 2 pi. The sine ratio repeats every 2 pi. Now what's n? N is an integer, okay? So we need to write that. N is an integer. Okay, so if you don't quite understand this, okay, we're at pi over 6 right now, right? And I could, if we're at pi over 6, I could go into a positive full rotation all the way, and I'd be back to here, right? And that would be still the ratio of 1 over 2 for the sine ratio, okay? I could go around twice, and I'm back here, and the ratio would be still 1/2. 3 times, 4 times, and that's what this n is. It's 1 time, 2 times. Now, what if I went in a negative direction? So I went 2 pi in this direction. Well, I'd be back to here, right? Okay, so that's why the 2 pi n, and n is an integer. N is an integer. Now, integers are the positive and negative counting numbers. So -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Those are all the integers, okay? All right, so any multiple of 2 pi with an integer will give me back this answer, okay? Or give me this as an answer, and it would give me the correct ratio, okay? We could do the same thing with 5 pi over 6. So x is equal to 5 pi over 6 plus 2 pi n. N is an integer. Let me go back and say this too. So how many solutions are there to this? Infinitely many. That's why we have to write a formula that generates all of them, okay? And then this would be x is equal to 3 pi over 2 plus 2 pi n. Because if we keep doing full rotations, we're back to where we started, right? All right, so, and we have to write this, n is an integer. You have to define what this n right here is. Okay, n is an integer. Okay, and let me slide this up. I'm sorry, you guys did not see that. Okay, so x equals pi over 6 plus 2 pi n is an integer. X is equal to 5 pi over 6 plus 2 pi n is an integer. X is equal to 3 pi over 2 plus 2 pi n is an integer, okay? And you'd have to write those, okay? You could just write this once and put, quotes down. That'd be fine. I would know what you mean by that, okay? All right, let's go to example number 5. I lied. I thought I had another example. I don't. Okay, so that's it for today. Okay, let me get the worksheet or the assignment sheet and we'll put that up. Okay, so what I want you to do today is I want you to solve simple trig equations, okay? And I want you to do worksheet TEI 3, and that's what I'm assigning today. And today's Tuesday. Today was the AP calculus exam, okay? I'm kind of excited. I want to see how my kids did today, okay? So you guys do this assignment so you're ready for calculus next year so you can get a 5 on the exam, okay? And that's it, okay? You guys have a great day. Take care. Bye-bye.